Good morning, Professor Wallace, Professor Wang, ladies and gentlemen, colleagues. Welcome to this peer distinguished lecture series. My name is Qingyan Chen, the director of the PolyU Academy for Interdisciplinary Research, or PEAR. So you probably noticed that we hold these peer distinguished lectures from time to time. And we always invite the most prominent scholars to give lectures. So today, I would like to invite Professor Zhang Kai-Wan, the Associate Vice President for Research from PolyU, to introduce our speaker. So Professor Wang, please.
Ladies and gentlemen, it's my great pleasure to introduce our speaker today, Professor Golden Wallace from University of Wollongong. Today is a Lantern Festival. I wish all of you joy, light, and fortune tonight. Having this lecture in one of the most important Chinese holiday will enlighten our path toward new discovery and innovation, especially in health technology. Professor Wallace is a world-leading scientist in health technology, smart material, and polymer system. He turns lab discovery into real medical devices that work naturally with the human body to heal and repair. Some of his most groundbreaking work, including 3D bioprinting and biofabrication, use patient stem cell and special Bionics to build human tissue and culture implant. He also is a pioneer in medical Bionics, creating material that help our body generate. One of his most famous inventions is BioPen, a hand-headed 3D bioprinter that let surgeons literally draw living stem cells onto damaged bone and cartilage. I just realized, there's another expert with actually the pain. Professor Zhang Hua from CTU, in his WeChat photo, he used the pain. I think for that pain, is not this pain. It's called phase engineered nanomaterial, right? Phase engineered nanomaterial. Hopefully correct, right? Okay. And if that's not cool enough, Professor Golden Wallace also developed eye fixed pen, which use a similar idea to repair eye tissue and restore vision. Beyond medicine, his research on materials like graphene is also pushing forward clean energy from solar cell to energy storage and solar to hydrogen technology. At the University of Wollongong, he leads the Intelligent Polymer Research Institute, turning cutting-edge bioprinting research into real-world products. His work has earned him some of the highest awards in the world, including the Order of Australia, Australian Laureate Fellowship, and the Eureka Prize for Innovation Leadership, as well as fellowship in top academy around the world. Ladies and gentlemen, please put your hands together and warmly welcome Professor Golden Wallace. Thank you.
Thank you for that kind introduction, and thank you for coming along to have a listen today. I'm definitely excited to be here in Hong Kong for what's really my first working visit or my first research visit, and I'm really looking forward to using this as a catalyst to build important collaborations as we go forward. Because I think what you'll see with this talk today is that hopefully there'll be some technical findings for you, but what's more important is the importance of building collaborations, building interdisciplinary teams if you're going to travel that discovery to deployment journey. So this is Wollongong. It's just south of Sydney in Australia, just 1 hour drive on the coast. It's a nice place to work, a nice place to live, and a nice place to do research, and a research that we hope will be translated into clinical application. So that discovery to deployment journey is one that not for the faint-hearted. and it's certainly not a journey that you want to travel alone. We've attracted many researchers from around the world over the years to help us on this journey. We've benefited from their knowledge and input into many aspects of the journey that we've undertaken. And you'll see that it's a complicated journey. And you'll see that we're learning all the time how we can execute that journey in a much more effective way. Critical to the areas I'm going to talk to you about today is the clinical expertise. Without the clinicians, without the surgeons and the practicing clinicians coming to us with the challenges, helping us articulate the challenge, helping us develop the plan, and then eventually helping us deploy the solution. Without their input, this would not work. It would finish with the publications, and it would not be translated into the clinic. So this story starts with Professor Graham Clark up there in the top corner. Graham is the inventor of the cochlear ear implant, the bionic ear. 22 micro platinum electrodes that are implanted into the cochlea of a profoundly deaf person. A microphone picks up the sound, stimulates the nerves through those electrodes, and enables profoundly deaf people to hear again. It's been an incredible success. Of course, it's a journey that took 40 years and is still ongoing, but now has been implanted in many patients around the world. We were involved in using organic conductors for a whole range of applications and discovering all of their amazing properties. When Graham approached us about seeing if those organic conductors could rival or maybe even replace the platinum electrodes in the cochlear implant. So began the journey of thinking about how we can develop materials and develop new fabrication protocols in order to tackle big medical challenges. So inherently conducting polymers would be known to many of you. They're basically polymers in every sense of the word that you would be familiar with in being lightweight and flexible, but with that additional dimension that they conduct electricity. And that ability to conduct electricity means that we can use them for many different types of applications. The one of interest here is, can we use those in order to communicate more effectively with biological systems? Starting with living cells, going through to tissue and through to real clinical applications. So inherently, they are compatible with biological systems because these materials are organic in nature, as is our biology, of course. And so we do have that inherent intimacy between these materials and biology. There's other things that are really peculiar about these materials, though, and that is they can be oxidized and reduced at very small potentials. And that oxidation and reduction process changes a lot of the properties of the materials. So as we convert between the oxidized and reduced state, we change hydrophobicity, so the contact angle changes a lot. We can generate ion fluxes at the interface, quite substantial ion fluxes. We can even change the topography. So by changing the potential, you can change the roughness of the surface. Now, the challenge with these materials is it's very difficult to isolate just one of those changes, and that they're all usually occurring in concert. And it's that concert of activity that probably gives us the unique combination that it results in unique communication with biological systems. So our very early experiments in this area took a ganglion explant from a guinea pig, the cochlear explant. We would put that on these materials, just two-dimensional material, and look at the effect of electrical stimulation on the ability to shoot neurites out of those nerve cells. That was a measure of the communication of our new material with this biological system. And we would electrically stimulate, and we would count the number of neurites and count the length of the neurites. We could also incorporate, because of the organic nature of this electrode, quite different from platinum, we could actually incorporate into the body of the polymer proteins that are known to be bioactive. In this case, NT3, neurotrophin 3, that's known to interact with these types of cells. And that combination of loading it up with biological activity and electrical stimulation enabled us to get performance that far outweighed what you could do with a platinum electrode. So we were to count the number of neurites per explant or the length of the neurites per explant. In all cases, the performance outperformed platinum. And even in animal studies or preclinical studies, in all cases and by all measures, these materials outperform platinum. But yet it didn't displace platinum. So it didn't find its way into a clinical environment. And there are various reasons for that, which we'll come back to. But one underlying reason is that to displace an existing technology, particularly in the medical space, you have to really outperform by orders of magnitude. So here's a material which gives us unique means of communication, but still not enough to displace the incumbent electrode platinum, at least not for now. Looking at that data, you remember all the neurites coming out of the ganglion explant? Well, looking at that data, another colleague of ours who's a medical doctor and a researcher, he's been working on schizophrenia for many years, how schizophrenia develops and how you might develop ways to treat it. So Xu looked at that raw data, remember all the neurites coming out, and he picked up a nuance that we didn't observe because we weren't looking for it. And that is that the degree of branching of all of those neurons also increases dramatically through stimulation through these particular materials. So we set about seeing if we could actually look at the effect of electrical stimulation to treat cells that have been exposed to schizophrenia. So these models were developed in Xu lab. They're mouse models which have particular genes knocked out in order to induce the characteristics of schizophrenia. So one's neuregulin 1 and the other is DISC1. You just need to remember that we've got cells that have schizophrenic behavior and wild type cells that don't have schizophrenic behavior. And you'll notice the experiment down the bottom is very similar to the experiment that we started with Professor Graham Clark. But now what we want to do is see if we look at our knockout cells where we expect the degree of branching to die back and the number of neurites to drop back because of the effects of schizophrenia, can we restore to normal behavior those cells through electrical stimulation? There's a little bit of data on the next slide, but let me just focus on the one on the right-hand side for me, which is the branches per cell. You can see that the wild type with electrical stimulation, there's a little bit of an increase in the branches per cell. But if we go to the neuregulin 1 knockout, you can see how that's all dropped down. The number of branches has dropped down because of that inducement of schizophrenic behavior in the cells. But electrical stimulation restores it back to the normal level. And it's the same with the DISC1 knockout as well. Now, that set of data to the uninitiated, like me, doesn't look all that exciting, right? For someone who's been looking for a cure for schizophrenia for 30 years, this is exciting. This is exciting. This is inducing behavior that he hasn't been able to induce by any drug combinations, by any diet combinations that he looked at before. And it's achieved through electrical stimulation through these particular materials. We can't do this with a conventional electrode material. So you'd think that with big advances, big discoveries like this, that we should be looking at how can we deploy this into the clinic today. And we are, but there's still some way to go. There's still issues around materials processing and scale up of device fabrication. We need to have a wireless stimulation protocol. And of course, that's becoming much easier now with very small implantable wireless stimulators that are being developed by various groups around the world, or even using a technique that I find quite fascinating. It's an electrochemical technique, but you actually drive redox reactions in an electric field. So there's no contact. The electrodes, the electric field electrodes are outside of the contact with the stimulating electrode, and that field still drives redox reactions. Coincidentally, the technique is called bipolar electrochemistry. And we're using it in our studies on schizophrenia. And I'll just give one indication here of what we're doing. We're taking our soft conducting polymer, you can see in the middle there, and now instead of putting wires onto that conducting polymer and stimulating the nerve cells, we just apply an electric field around that conducting polymer, and we can still get the same effect in terms of stimulating the nerve cells. So slowly we're knocking off all of the things that are required in order to get us closer to clinical deployment. But there's a few other issues, and I touched on it a little bit when I talked about the comparison of platinum and a new electrode. Regulatory issues are really difficult sometimes to confront when you're introducing a brand new material into a medical device. All of the economics around replacing platinum or some other electrodes are going to be difficult, and then there's the commercial model as well. So for replacing the electrodes in a cochlear implant, that looks a little bit daunting because there's already a solution. But for generating electrodes that can treat schizophrenia, there is no alternative. 30% of schizophrenia patients can't be treated by any other method. So in the pursuit of various areas of application and in listening to collaborators, and in particular clinical collaborators, we've been able to identify an application which must be translated into the clinic, and those issues must be addressed because there's a lot of patients that need to be treated using this particular approach. I'm going to change speed a little bit and have a look at graphene. It's another organic conductor. The way that we produce graphene is pretty crude. Sorry, Dan and Joe, but it's a very sophisticated approach, sorry. So as we take graphite and blow it apart in strongly oxidizing conditions, in so doing, all these little red oxygen atoms appear on the graphene sheets, so we end up with graphene or graphite oxide. And then we judiciously remove those oxygen groups so that we can, it's a delicate balance. The more we remove, the better the inherent physical properties of the graphene, for example, conductivity, electrical and thermal, but the less processable. So it's a delicate balance. We need to remove just enough oxygen groups to maintain processability, and yet remove enough in order to get the properties, the physical properties that we want. And that first part, that step of blowing it apart, also enables us to remove impurities. And I just put this slide in because it emphasizes an important part here. And particularly when you're going into medical applications of materials, you need to be able to control the source and you need to be able to control the purity. Now, depending on where that graphite comes from in the first place, it's got a totally different composition depending on its original geographic source. And there are some sources that have silica, for example, as a major, let's call it impurity, but it's a natural component of the graphite, and it's really difficult to remove. But I just use it as an example to highlight, that the sourcing of materials for medical applications is critical. And you've got to get it right at the start, because all of your subsequent experiments on that material are what's going to be used to give evidence to the regulator in order to get your device approved. And so this is a really critical thing that we certainly missed in the early days of thinking about medical applications. This is work that Dan Lee did, and Dan is here, looking at that exfoliation process and controlling the exfoliation and the subsequent reduction to get rid of the oxygen atoms, so that we ended up with a highly processable aqueous dispersion of the graphene. Now, this was a major breakthrough. It's exciting science and exciting discovery, but it's the implications of the science and the breakthrough that are even more important, because it meant that we could process the graphene into different shapes, different forms, and actually fabricate structures containing that graphene. There were various ways to do that. So it wasn't just this fundamental discovery and the understanding of the structure of the graphene and the oxygen atoms and how to remove them and controlling the pH as we remove them, but it was the implications of that, the fact that we could now spray graphene onto other surfaces, we could spin fibers, we could print it, and we could even 3D print structures, and we did this for some of our biomedical applications. And this project is really accelerated in recent years. It's using graphene for bone repair, graphene combined with other biomaterials for bone repair, being led by Dr. Xiao Lu in our laboratories at the moment. So a fundamental breakthrough in the materials and understanding of the materials catapults advances in processing, which catapults us towards real biomedical applications. If you control that process in a different way, you can actually get very large sheets of graphene oxide as well. Remember that picture of them all falling apart? Well, of course, all the sheets are different sizes, and And you can control that process to try and get larger sheets of graphene. And that was important because those larger sheets, and I think Joe was involved in this work, those larger sheets, yeah, there. I see your name there, Joe. I just had to check that. Those larger sheets then can be used to form liquid crystalline dispersions of the graphene oxide. So again, a really interesting and exciting scientific discovery, but you get doubly excited about the implications of that scientific discovery, because that meant, because we could form liquid crystalline dispersions, it meant that we could control the rheological properties of the graphene dispersion. And the rheological properties, of course, dictate what type of processing, what type of fabrication we can use to create useful structures. So Joe was involved in setting up a lot of our early wet spinning protocols where we take those dispersions. So let's take that liquid crystalline dispersion where it's very stable in the aqueous media, but you can squirt it or deliver it into a media where it coagulates, and that might be through changes in pH or ionic strength or a different solvent, for example. And in so doing, you can create very long lengths of fibre, of micro-dimensional fibres using this technique called wet spinning. And we use those fibres for a range of applications in the energy space, particularly for energy storage. But let me tell you about a recent development using fibres that are based on their fabrication using this type of technology. So this is a highly flexible fibre, very fine. It's all based on graphene. There's a very, very thin layer of platinum introduced as a current carrier. And one of the features of these graphene fibres is that you can tie them in knots without changing any of their electrical properties. You might think to yourself, well, why do I want to tie an electrode in a knot? Well, that's a very good question, and I didn't have an answer to it. But the student that developed this got incredibly excited. And so, of course, the rest of us got excited as well. In subsequent discussions with another colleague of ours, Mario Romero, and Mario and I, both our groups, have been interested in the development of electroceuticals. So think back to schizophrenia. It's really an electroceutical approach to treat the schizophrenia. Mario is interested in the use of electrical stimulation of nerves going into the spleen in order to control the immune response and any diseases associated with that immune response. And so Mario got hold of our fibres and realised he could do something with those that he couldn't do with traditional electrodes. And it all involved tying them in a knot. What Mario was able to do just in that bottom left-hand side is to tie these electrodes around very fine nerves going into the spleen. So before this development, you could not interrogate those very fine nerves. The only nerves that could be incorporated or interrogated were further up the stream. If you can just see VN in the top diagram, that's the vagus nerve. And so in order to regulate the immune response, people had been stimulating that very core nerve structure. And sometimes it worked and sometimes it didn't in terms of regulating the immune response. And Mario, using those electrodes, was able to unearth the reason why. You really needed to get down to the individual nerves going into the spleen, SP1, 2, 3, etc., and stimulate those nerves in order to have the fidelity of communication that's required in order to control that immune response. So this is an interesting twist, and I think we find it more and more. Some people say, you can't get involved too much in translational research because discoveries are important. And I agree, discoveries are important. But translational research can actually push you to make discoveries that are fundamental in nature. So we would consider this a translational experiment. The truth is it was also a huge discovery experiment because Mario then unearthed that he could monitor how organs communicate with each other through looking at these nerve stimulation experiments and do fundamental exploratory research that wasn't possible previously before these materials were developed. And so that push towards translation also unearthed some pretty amazing discoveries if we can close the loop in an appropriate way. I'm just going to check. Perfect. On time. Let me just mention one other form of graphene before we move on to some other areas, and it's an edge functionalized graphene. I mentioned this is exciting. Again, you know, it's easy to get excited about this work because it encompasses fundamental discoveries, and then you see how they can be used to create real solutions. So remember that the video of the sheets flying apart and the oxygen atoms, and we had to take some of the oxygen atoms off and keep processability, but try and get the physical properties that we wanted. Well, one clever way to do that is if you could take the oxygen atoms selectively off the basal plane and leave the oxygen atoms around the edges of the structure, so-called edge functionalized graphene, because that gives you really high processability in the aqueous media, but also in organic media, and yet gives us also the high physical properties like the conductivity properties that we want. So I'll just mention that we've worked on that. We've processed that, soluble in a whole, dispersible in a range of solvents, which are very stable, enabling us to make medical composites, which are closer to clinical deployment, particularly for nerve stimulation. So in that area of organic conductors, we don't have anything that's been used, or we don't have anything that's scheduled for a clinical trial at the moment, but we're getting much closer. And the reason we're getting closer is because we're developing better ways to process the materials, simpler ways to process the materials, and finding applications that can't do without these materials. There'll be many applications where we could do things a little bit better by improving electrical stimulation. But if there's already a solution, it's going to be very hard to displace it. But in the schizophrenia case, there is no solution. So we don't have to displace it. We just need to tackle the practical things that we need to tackle to bring it to clinical deployment. And that's all of these. We need to be able to tackle all of these together. So when we say interdisciplinary, we don't just mean scientists and engineers, biologists, and clinicians. No, the list goes on further than that. It's people who have expertise in regulatory issues, expertise in developing health economic strategies so that you can convince people this should be deployed in the clinic, and to be crude, the appropriate commercial model, because if it doesn't get commercialized, it won't get deployed in the clinic. Now, we learned all this over a number of years. I probably should have read the foreword to our book a little bit more closely. It was written by Professor Graham Clark. And he said in that book all those years ago that one of our challenges would be material processing and device fabrication. So Graham had traveled the journey, the discovery to deployment journey, and could see where the roadblocks might be. And sometimes it's really important on that journey just to slow down and to listen to your collaborators and really analyze where you want to go and what you need to have to get there. Because just doing one experiment after another is often not the solution to deployment. Let me go back to clinical expertise. And I want to tell you a couple of stories that involve Peter Chung. He's an orthopedic surgeon. And also Toby Coates, who does islet cell transplantations. I've mentioned a couple of these people already. And Fiona Wood, who works on skin regeneration and wound healing. Let me start with Peter Chung, orthopedic surgeon. He's often removing cancers from bones. In so doing, he damages a lot of muscle and bone and cartilage. And so he's pretty interested in better ways to restore that cartilage. And also, a lot of these injuries occur when you're young. 20 to 30, you'll get that little niggly hole in your cartilage. Now, cartilage is that cushioning material between the bones, which means that you can move without hurting yourself, right? And when that cartilage gets damaged, eventually you end up bone on bone, and you can just imagine what that sounds like. If you haven't heard it, I'd recommend you don't listen to it because it's excruciating, the pain that these people must be going through when bone is on bone. So cartilage repair is really important. Now, Peter approached us a number of years ago, said he had a couple of programs in his group. One was looking at chitosan, to catalyze cartilage repair. The other was looking at stem cells to catalyze cartilage repair. And we decided to combine those using a 3D bioprinting fabrication approach in order to accelerate cartilage repair. And it worked very well. We could take chitosan, we could take stem cells from the fat pad behind the knee. We could combine those in a printing technology and regenerate cartilage on the bench. Now, to get us closer to clinical deployment, Peter wanted to, so this is really his invention, because he asked for it. He wanted to be able to print into the defect in the knee because he thought that that would be a better way to deliver the biomaterial and the stem cells. So we did develop the BioPen. It's a coaxial print head. It's got the cells going through the middle of the core, and then you've got a material that wraps up the stem cells as you print it into that defect in the knee. This actually catalyzed some debate between the clinicians and engineers. You don't, in these collaborative teams, you don't agree all the time. Right? So that's all right. It's okay to disagree. So Peter's version, and this is serious. This is his ideal printer, right? So when we first sent him the handheld printer, it had like 6 controls on it. And he said, far too complicated for the clinic. He said, in fact, 2 buttons is too much. I want 1 button. It's on off. Of course, the engineers, we got down to 2 buttons. He wants 1 button there. But we assured him that we could organise training courses for surgeons that would enable them to handle 2 buttons. So we did that. And in fact, it did catalyse an alternative research program in our group, which is looking at robotic 3D printing directly into the knee. And by the way, this is top secret, because if this gets out, none of the surgeons are going to talk to me again, right? So this is our secret project between you and I and whoever's listening on YouTube around the alternative to the 3D bioprinting in the surgery. But Peter was right. The ability to print into the defect in the knee produces much better results than pre-printing a scaffold and then placing it into the knee in terms of cartilage regeneration. So we have an elegant approach here. We've got a pen, we've got the materials, coaxial, we're growing beautiful cartilage. Here's our clinically deployable solution. We're going to take that sample from behind the knee, we're going to process the cells, come back and put them in again, and then the regulator comes along. So, no. You can't do 2. You've got to do it in 1 surgery to make this economic. So what was taking 8 weeks to prepare the cells, we now have to think, well, how do we do it in 6 hours? Because that's the one surgery. So, and that was a real turning point just a few years ago. We thought we were ready to go. We thought we were ready to go into the clinic with that 2-step solution. But we were really fortunate that we had a person join our group that was previously with the TGA, FDA equivalent in Australia, and looked at the regulation and was able to help us understand the way we needed to do this to get it clinically deployed. So we've spent the last couple of years working on that part of the solution, reducing that time to produce the solution in a 1-step surgery. And I'm pleased to say that combined with all of this expertise, we're now ready in the second half of this year to go to the first in human clinical trial with that cartilage regeneration solution. But it's been a twisted journey. And, let's face it, if we had had the regulatory input earlier, we probably could have switched earlier and we could have got there sooner. So the earlier we can get that non-technical expertise into the project, the better. We go to islet cell transplantation. Islet cells taken from a donor, they're implanted into a patient in order to treat diabetes. Toby Coates approached us because a lot of those islet cells are lost during the initial injection into the patient and afterwards due to the immune response. Toby wanted us to develop an encapsulation method for the islet cells, protect them, protect those precious cells, and then support them with T regulatory cells to fight off the immune response and also other cells that would help us catalyze the growth of the vascular system to keep them alive. So we've done that with Toby and his group over the years. We've developed a bioprinting approach to create these scaffolds. We're looking at transplanting them just directly onto the skin to treat diabetes. So this will be a system that preforms the structure using a simple 3D printer on the bench, and that 3D printed structure contains the islet cells that are protected in a wraparound material. It also contains the endothelial cells to help grow the vascular system, and also the T regulatory cells to fight off the immune response. This is some very recent results that just focuses on our ability to create the vascular system that will support the islets. And this is some animal work was just completed with Toby and his team. An interesting project because Toby came to us, the clinician came to us with a very well-defined challenge. He knew what cells he wanted in the structure. He knew where they wanted to be. And we just had to build the structure that would accommodate that and to provide a better transplant vehicle to treat diabetes. So just reminding you that checklist still exists for all of the different projects. There's technical and non-technical issues that we need to address. I'm going to go quickly through cornea and skin, so just hang with me. Just take a deep breath now because we're about to go a bit faster, right? So cornea, leading cause of blindness, solved by getting transplants from a donor. There's some 7 million people on the cornea donated waiting list. And so I was approached again by a clinician saying, here's another simple challenge. This one's not so simple. Why don't we bioengineer a cornea? You know, we can get the 3 different cell types, get the collagen structure, and we can build it in the lab. And then, you know, we put it into those millions and millions of people that are waiting for a donated cornea. I'll just focus on one point here. Endothelial, epithelial layers, the top and bottom. Okay, we can grow those cells. The stroma, that middle bit, it's about 400 micron. It's a very sophisticated piece of machinery. It consists of a whole lot of collagen layers. Each collagen layer has aligned fibrils within it. And each layer is at right angles to the layer below it. So you wonder, how did that structure ever evolve? Right? I mean, obviously, it evolved over time. It evolved over time, but now, you know, we've got a clinician saying, well, look, it evolved in millions of years, but, you know, you can create it in a year, you know, so, but it's challenging. But we have developed some very interesting ways to create those aligned structures. So we take collagen molecules. Here comes the electric field again. Remember that electric field driving reactions that we touched on before? But now we're using the electric field to coagulate, if you like, our collagen into these aligned fibril structures. And see, and that alignment and that orthogonal arrangement is critical to getting the combination of transparency, robust physical properties, and biological activity. So we can do it. You know, you can do this. You can grow it on a bench, and it doesn't take a million years, but it takes a long time. And so now we're charged with, if this is going to be deployed into the clinic, can we develop an automated manufacturing method that will basically produce bioengineered cornea that we can deploy around the world? And it is complicated, right? We get a donated cornea. We have to extract all of the cells, epithelial, endothelial, and the keratocytes. Collagen comes from skin or placenta. We have to extract that. And then we start fabricating. So it's complicated, but we're doing it. We have a very large medical research future fund grant, an amazing team of individuals that have come together to embark on this challenge. And along with the whole fabrication and manufacturing method, the challenge of actually carrying, and I put this in because I'm hoping that somebody in here or out there has a solution to this problem. We're getting closer, but you think about it, we're building a cornea that's got all of those cell types, and now we go to the regulator, and the regulator says, well, how do I know what you've got? And how do I know what you've got every time you make it? So you can't use conventional biological techniques because that involves taking it apart. So here's the challenge. How do we develop non-destructive, non-contact characterization tools that tell us that we really do have a bioengineered cornea? Now, we're working on various techniques here. I'll just throw in ultrasound as one possibility. But if you've got any better ideas or even complementary ideas, we're all ears. We'd love to hear them. Because this is a real challenge. This is a real challenge for any bioengineered product that needs to go into the clinic, where you have to preform and pre-make the product. You need to have characterization tools that don't destroy it and will convince the regulator that that individual component that you're about to put into an individual human being is actually what you think it is. So it's a big challenge. And part of this is, and of course it requires an incredible team to come together to make it work. I'm going to finish on skin regeneration just quickly. Fiona Wood developed a spray-on skin back in the time of the... Fiona is famous for her treatment of many patients, many Australians in the Bali bombings of some years ago. Fiona was Australian of the Year for those advances in her ability to treat those patients. There's a real need, still a real need. When you've got deep wounds that come from burns, we still don't have an adequate means of treating those patients. So let me cut to the chase and tell you where we are on this. We're looking at a molecule from seaweed. This is a seaweed farmer that we work with, Dr. Pia Winberg. She lives just down the coast. Pia provides this unique species of seaweed, which produces this unique class of ulvan molecules. And those ulvan molecules have been shown in our constructs for wound healing. They've been shown to improve mechanical properties. So just the addition of small amounts of this molecule can change mechanical properties. And that's important because one of the real drawbacks of current treatments is you get a lot of scarring. And that's because of contraction of the skin. And so anything that can provide mechanical robustness is important. But of course, providing that at the expense of biological activity would be counterproductive. And that's usually the solution. Usually the molecules we introduce to improve strength or durability or some other mechanical property, they compromise the biology. So if you can find a molecule, and we were lucky enough to do that, if you can find a molecule that improves the mechanical properties, but also can control and activate the biology, you're onto something exciting. So we're using that molecule from seaweed, using that in combination with a source of cells that Fiona developed, the ReCell, the spray-on skin, and her very pragmatic approach to getting something into the clinic quickly. So this project came along at the right time. It came along when we had a source of cells, we had a clinician that said to us, I understand the regulatory aspects of this. If we're going to do it, let's do it this way. Keep it simple, keep the solutions and the formulations simple, and we can get it into the clinic. We can continue to develop and improve on those materials and those cells. But when you work with these clinicians, you really get the message. We don't have time to sit around and come up with the ideal, optimal solution. In some of these areas, like in the schizophrenia, like in the cartilage, in the islet cell transplantation, and the cornea and the skin, there's people waiting for this now. They need a solution now. It might not be the ideal solution, but let's get together a solution which we can get regulated, we can develop the right health economic models and the commercial models and get it into the clinic. That doesn't stop us getting better things as we go down the track, but these people need something now. So let's simplify our thinking and get that solution into the clinic. And you'll see that all of these case studies have simplified that thinking on the journey. Some simplified the thinking earlier than others, but all of them have simplified the thinking in order to get deployment. I'm out of time. It's like landing an airplane. Signs keep coming up at the back. Thank you very much. So let me I'll just give you one example of this. Here's another really simple example of changing tech for deployment. This is some work we're doing with Jilin University. I'll just give you one example because it's in the wound healing area. Electrical stimulation can promote wound healing. The delivery of certain things into that environment promote wound healing. What about this for a really simple, elegant, and exciting idea? What about we create a biobattery, an implantable biobattery, or a battery that we can put on the wound, and that biobattery provides electrical stimulation, but it also provides products from the anode and cathode reactions that facilitate the biology. So with an ex-student who's now at Jilin University in China, we have been developing this biobattery concept. It uses a conducting polymer as one of the electrodes. It uses magnesium as another electrode. And so the electrical stimulation on this very simple device can promote wound healing. But what you wouldn't have thought of, or I wouldn't have thought of, smarter people thought of it, what people have thought of is that at one of those electrodes we generate hydrogen. Now, you didn't know small amounts of hydrogen in a biological situation are excellent, anti-inflammatory, can really help the wound healing process. At the other electrode, we're generating magnesium ions, again, to facilitate the wound healing process. So my wrap up before the 1 minute sign comes up is connectivity. I said right at the start, I hope there's something technical in here for you. I hope there's some ideas that spark other ideas that get us better solutions to some of these big medical challenges, all for better solutions, and all for working with whoever we can work with that can contribute to advancing these challenges. Because as all of those clinicians keep saying, we need to do better, and we need to do better now so that we can deploy things into the clinic. We can continue to refine in parallel, but we have to have all of those connections that are necessary to make sure we can advance. So this is the road into Wollongong, actually. So when you come over to visit us, come from the airport, you can come down this road. It's a bit windy and turny and scary at times, a bit like the old discovery to deployment journey. It is scary at times. It's not a journey, I said it right at the start, I'm going to say it again. It's not a journey you want to take alone. It's not a journey that you can take alone. There's no one individual or no one group, I would hasten to say, unless it's quite big. There's a critical mass issue here that's going to consume and provide all of that expertise. So how do we get it? We get it through connectivity, we get it through collaboration, and we need to get it as early as possible. I think thinking that we're going to design something and then walk up to your clinician and say, what do you reckon? We stick this into somebody next week? No, not going to work. In fact, they won't even talk to you. But we've got to be asking the clinicians, what's the challenge? What do we have to solve? We go away, we solve it together, and then we deploy it together. Training in an environment like this is exciting. You know, when I did a PhD, you don't want to know when that was, but when I did a PhD, you know, it was kind of frowned upon if you talked to other people about what you were doing. You know, and certainly you didn't talk to anyone, you know, in biology, for example. There was, you know, funny people down the end of the corridor. But it's changed, right? This is exciting. People can do a fundamental project at one end of the laboratory, and they certainly can on our innovation campus. They can be doing a discovery project here, and they can look down the end of the corridor and say, hey, these things are getting deployed. These things are getting used. Clinicians are coming through all the time, talking to them about their approach, talking to them about the challenges. That's an environment that you want to be doing research training in, an environment that understands the whole process and helps people find their niche in that process, because it's not for one individual to travel the whole journey, but just learning how we can travel that journey together. So at the core is technologies and cells and materials, clinical, commercial, regulatory matters, and social engagement. You know, time's up. Oh, shit. Okay, hang on. I'll only be 30 seconds. So that was abrupt. I didn't see the 1 minute, so I got too excited. I'm sorry. So social engagement. You know, going back to Graham Clark's story, you know, the inventor of the cochlear implant. You know, some of the strongest opposition to the cochlear implant, the deaf community, because they felt that technology was replacing something that was precious to them. And if you read Graham's book, he talks about that in there. So how important is it that we don't just talk to clinicians, we talk to patients and patient advocacy groups. We need to know that we're developing a technology that people want to use, that it's not going to be forced upon them. So that social engagement is really important. You know, if we get all of that work, and that machinery can be beautiful. We can take discoveries, we can take them to deployment, we can do it in a reasonable period of time so that patients can benefit from those discoveries. And that's what we're here for. And it's certainly what gets everybody, because look, we all know research can be not so exciting sometimes, right? It can be frustrating sometimes. It can be difficult, but it's worth it. If we're going to deliver things that really help patients at the end of the day or some other aspect of our community, then it's worth it. Thank you very much for your attention. I think I've finished just on time.
Good morning, everyone, both in this seminar room and also online. My name is Lianzhi Wang from the Department of Applied Biology and Chemical Technology of the Hong Kong Polytechnic University. It's my great honor to chair this discussion session. First of all, thanks Professor Gordon Wallace for the fascinating talk, wonderful. And I attended many of Gordon's talk before, but every time I learn a lot. So so today actually you covered, so many aspects from the fundamental, discovery of the material and to the processing, characterization, and to the long journey of clinical trial. And it's certainly a wonderful, journey and to share and to experience. And another thing I want to say, actually, Gordon is not only one of the most influential, research in Australia and also broadly, global and in the nanotechnology field. He is also a wonderful, great mentor. And if I just want to name a few, within this seminar room, we have at least 5 chair professors who have worked or who have collaborating with the Professor Gordon Wallace in the past, like Professor Dan Li from Hong Kong University of Science and Technology, and Professor Zeping Guo and Professor Shujun Zhang, and also Hua Zhang. They all global, STEM professors, and from CTU. And we also have one, Professor Joe Rizzo had been working with Gordon in the past, now professor at Hong Kong Polytech. Basically, you train a lot of good professors in Hong Kong now, including me. Yeah, and so you have trained maybe more than 100, I would say, a few hundred. Yeah.
PhD students, yes. 200.
200, yes. So, and it's very, very influential, and also for the the future generations, researchers, certainly we benefit a lot from you. And I think I had enough. And now I think the floor is open for questions. And we first welcome the questions from the room. Who wants to start with? You can push the button, and so just in front of you for the microphone. Yeah, please.
Thank you, Professor Golden. Thank you for your fascinating presentation. I'm a PhD student in biomedical engineering, and I also have a clinical experience on neurorehabilitation, especially schizophrenia, and I kind of use some TMS, transcranial magnetic stimulation. So you mentioned that in the clinical finding that neural branching with electrical stimulation in knockout mice. And my question is, do you think the key to moving from this model lab effect to a clinical therapy for treatment-resistant patients lies in achieving more target spatial resolution or in developing novel stimulation waveforms that those new materials can uniquely deliver? Thank you.
Yeah, thank you. There's an ongoing program looking at different materials and different growth factors, for example. I think that can happen in parallel. I think the only remaining hurdle to getting it into clinical deployment is an efficient wireless stimulation system, so that we're not having to cross the skin barrier. And I think, and as I mentioned previously, that will not be the ideal case, and that will not be the ideal solution. There's no doubt it could be improved, but if it provides some improvement to those people that can't be treated at all at the moment, then my colleague Shufeng Huang, who's the MD involved in this, is convinced that we should go with that treatment for now, while we improve all of the other aspects. Oh, and you mentioned even the waveform that we use for stimulation. There's no doubt that could be tuned, and and the number of variables in there is huge. But they're all studies that we'll undertake in parallel with getting the minimum viable product available as soon as possible.
Thank you so much.
Any more questions? Yeah, please.
Thanks for your presentation. My question is about the electrical stimulation using the conductive materials. Actually, we do have many different ways to apply electrical stimulator now, like piezoelectric effect and the triboelectric effect. So my question is, what is the advantage of conductive materials for applying electrical stimulation?
So you're right. There are various ways to induce electrical stimulation. I think there's something, whichever way you induce it, these organic conductors have particular interaction capabilities that I would say we don't totally understand. I mean, the fact that you can get unique responses out of those cells in the schizophrenia studies that you can't do with other metal electrodes, or even get unique responses out of the ganglion cells, indicates that the material itself is engineering or controlling the cellular interactions. So whatever way you deliver the stimulation, whether it's piezoelectric or triboelectric, the material interface is what's important. And I think these organic conductors provide a unique ability to control that interface, and the unique ability to tune it in situ through electrical stimulation, not just providing current, but providing changes in the topography, changes in the modulus, changes in ion fluxes. So does that answer the question?
Yeah. Okay, thank you.
Thanks.
Any further question? Or I can maybe ask a couple of questions from online first, and then you can think about, and then next round maybe ask you two. So the first question from online is, how can we draw inspiration from nature to construct the physical device? And this one I think also can be combined with another one just come onto the screen, is how to design the biodegradable and biocompatible materials who have the good mechanical property and also can have beautiful by sort of signal connection.
That's a big question. So let me start with the inspired by nature, because I think it does touch on the others. Obviously, in the area of the organic conductors, they are synthetic materials, and I think in terms of their combination of chemical, biological, and electrical properties, I don't think there is a natural equivalent of the organic conductors. But going through, but if someone knows one, I'm happy to learn. So please tell me. And then in the other areas of the tissue regeneration, you might notice that we've always reverted to, we haven't always started with, but we've always reverted to naturally occurring materials, using the collagens, using the chitosanes, using the materials from seaweed. That could be alginates, or it could be ulvans from the green seaweeds. Those materials just have an inherent compatibility with biology. And if they work, I figure, why re-engineer what nature has taken many, many years to optimize.
Excellent. Any further question from the room? Yeah, Shujin. Yeah.
Yeah, thank you, Angel. Yeah, hi, Gordon. Very, very good talk. So I think your research really interdisciplinary and multidisciplinary. So to build such a team is very tough. So just like my question, want to get your comment because last time I talked to Professor Shifeng Wang about that, but it looks like just the chicken talk to duck. It's so difficult to understand from different research fields. So for your comment, if you want to build up as a multidisciplinary team for doing research to guarantee the success, so how do you think the team member need to learn something from the other parties, at least to understand some background of their knowledge or blah blah like that? So what's your comment for this kind of team? Thank you very much.
It takes time and a lot of patience, and that's patience, not patience. In the clinical sense. And look, I don't know how you find the right people. When I put up that slide of the clinical connections before, every one of those clinicians that we work with is totally dedicated to the research, totally dedicated to finding solutions for their patients. And I'm told by others that those types of clinicians are pretty hard to find because they're so busy. Anyhow, so I think but it's using existing connections, right? So Graham Clark, our first clinical collaborator, Graham introduced me to Peter Chung, the orthopedic surgeon we work with on cartilage. He introduced me to, I didn't talk about it today, but to Mark Cook, a neurologist that we work with on epilepsy. Mark and Peter introduced me to some of the other clinicians, and so it grew over time. It was, introduction by personal introduction. So I think it takes time and it takes energy and resources. And that's a conscious decision that people need to make because it obviously detracts from something else. If you want, it's easier to do the short-term thing, right? And just do the work, do the research, do the publication, submit it, get the publication. But that's never going to get translated. Never. Right. So and not everybody wants to do this, right? But if you're going to translate in this medical field, you have to invest the time in building those interdisciplinary teams and building those relationships. And the other thing is that our organizations have to understand that it takes time, right? If all our universities are doing is measuring people based on number of publications and citations, that will never drive translation. We have to understand there's other things that need to be done. People need to be acknowledged for it and applauded for it. And particularly for younger researchers, we need to get them into existing networks as quickly as possible. So we run a network in Australia called Beyond Science, and myself and a clinician and the ex-chief scientist of Cochlear. And it brings together scientists and engineers and young clinicians as part of the network a number of times a year in order to build those links early. So I think for those of us who have connections, that's a very valuable thing to be offering to the next generation of researchers. If you need connections in that area, yeah, let's set it up for them. Let's make it easier than it was for us to have to go through and build it all over many years. A lot of the networks are there. Let's give the next generation access to those networks.
Thank you very much.
Thank you very much. I think that's a wonderful talk and wonderful answers. And this also related to some of the questions from online. They said, what's the most likely pathway if you want the technology to be translated and to the clinical? And this also some question related to this one. It's like the biosafety and also the standard protocol and photo from the lab to the clinic, and maybe you can also briefly address on this.
Yeah, so there's a very well-defined protocols in most countries for getting from the lab into the clinic in terms of regulatory and in terms of the types of preclinical and then clinical trials that you need to do and the documentation all around that. I mean, that's all available. But being available, of course, doesn't mean anything if researchers don't go and find it. because a regulator is not going to come and find you and say, oh, listen, do you want my book of regulations? This might help with your research. So we've got to go. We have a responsibility as researchers to go and find that. And like, that's easy for me to say now because I wouldn't have said it 40 years ago. Right? I always thought that those aspects were somebody else's responsibility. They're not. If we as researchers don't ask the questions, we'll never form the links, we'll never get the information. And in terms of the pathway to deployment, it all starts with defining the clinical challenge. And then right at the start, thinking about, well, what's the most likely way I'm going to get this regulated? If it's not using new materials, then avoid new materials where it can be avoided. But I think it's just understanding all the challenges at the start. And you can't get all of that as part of your own group, but go out and talk to people, I mean, go to medical conferences and present what you're doing at medical conferences. I mean, that's what we did, and we very quickly got the feedback. Not all of it was positive, I must say, but some of it was. But, take yourself outside of your normal sphere. You don't have to go to materials conferences all the time or, to ACS meetings all the time. Get out there and go talk to different communities. Tell them what you're doing. And you'll be surprised that, like I've given presentations at eye conferences, at knee conferences, cartilage, bone, and you'll be surprised how welcoming those clinicians are. The fact that, because otherwise they don't know what we're doing. I mean, what a waste. What a waste to have all of this research going on and the people that can use it don't even know it's happening. So we've got to get out there and do that.
Yeah, thank you very much. I think that's a very clear message and wonderful advice to the young generation and young talent in this room and online. Also to me, I think.
And me too.
Get out of your comfort zone and then talk to the other peoples. Yeah. Any further question in the room? Yeah, okay, Joe. You're challenging your former supervisor.
Yeah, thanks, Gordon, for coming to PolyU. Really a privilege to hear your talk, and also a privilege to have worked with you for a very long time. And now I think we're going to start working again. But probably the question is on behalf of the students in the room. I can see quite a few students here. I know some of the students here, and especially students who are probably working on material science or the non-medical field. And when they have projects that are related to, say, medical aspects, it can be daunting to be working with clinicians, especially when you don't know how to ask the right questions. So probably the question is, what are the tips for the students to be thinking? How should they think? How should they ask the right questions? Or not necessarily the right questions, the questions that must be asked to the clinicians.
Yeah. Look, it is daunting. My daughter tells me that she's the only biomedical engineer in the family because she did a PhD in biomedical engineering, and she was working on the skin regeneration project, and that was the most difficult part for her to get her head around, was talking to the clinicians and getting the feedback, because everybody wants to look prepared and look good. I think it's not so much how do you present to the clinicians about what you're doing. It's how do you listen really well to the clinicians? How do you just let them know that you're really interested in their problem, right? Because they don't care how it's solved. Graham Clark didn't care that we worked on conducting polymers. He just wanted a better electrode. He didn't care what it was. And he told me that many times. So clinicians are not going to be necessarily interested in your technological solution. They're interested in the fact that you want to understand the problem and that you're going to go away and think about it and then come back and say, well, what about this way to do it? Or this way to do it. And inevitably they'll say, oh, that's too complicated, or that's never going to work. But I think it's really starting that conversation and understanding that you're building an ongoing conversation. You're not going to get all the information in one meeting, but what you want is that clinician to want to talk to you again, right? So that's how that's got to finish up every time, that you're really concerned and genuinely concerned about listening and understanding their problem, and you're going to look for the best and simplest solution to answer that problem and work with them in developing it. You're not going to go away and develop it by yourself. You want to work with them to develop it, and then you're going to work with them in deploying it. And when I say you, I mean you as a part of a group, not as an individual. So I think asking and really listening is the first important part. But going up and saying, "Well, this graphene, mate, this graphene's wonderful. You wouldn't have seen anything like this before. This is beautiful stuff." And he's going, "Yeah, how's it going to make somebody hear better?" You got to come not with the material science. The material science is important. You've seen that in every case, right? The material science and the fabrication method, they all helped realize the solution. But to the clinician, it's the solution that's important. And the more that you're involved in this game, to me also now, it's the solution that's important. I'm also agnostic about how we get there. I'm not locked into any particular type of material or particular way that we make things. We just got to get something together with a clinician that can be used.
Thank you. I think another question from online is related to the material, and I think maybe challenging question. What's the strongest, lightest, and the non-brittle material available on the market?
No idea. Anybody else know? I mean, of course, you often read those words in graphene brochures,
yes,
right?
That's the thing that, yes.
But I mean, even still, and others, please do comment on this. At the moment, the reliable, let's take graphene as an example, and they do use terms like that, but reliable supply of reproducible quality graphene commercially is still a challenge. And that's certainly true if you're thinking about using it for medical applications, because every batch, everything's got to be exactly the same every time you do it. So I don't know if they're referring to graphene, but I know a lot of my colleagues that work on graphene use those sorts of words. So maybe it is.
Yes. Any further question in the room? Yeah, please.
Hi, I'm Elmer from Biomedical Engineering. I was just interested to know what was the greatest challenge you faced when you were doing the translation?
Oh, just one. There's many. Not really a challenge, but something we should have done differently right from the start. And I can always make the excuse we didn't have the resources, but that's not a good excuse. Is that we should have had much more input into our research plan by people who weren't part of the research plan. So in other words, people that understood the regulatory, understood the health economics, understood the manufacturing and scale-up challenges, processing challenges. So they're all challenges. There's no one single one that stands out, but I think there's a common theme, and that is understand the challenge early. And if it's insurmountable in your lifetime, well, find another way to do it. Because there's always other ways to do it. I really encourage our researchers and our younger researchers in particular to think about getting the solution in the best way possible. So I think if we can grasp that challenge early. Now, of course, a PhD student, you've got your supervisor to deal with as well, but you can deal with those most of the time. Because you might come up with a better way to do it, and tell them. And I'm sure that most people will listen and appreciate the idea and adapt accordingly. So, understanding what the challenge is early is really important. and then communicating better solutions. If you have one, talk about them, bring them up, and go and tell your supervisor. I mean, when the guy came and he could tie that electrode in a knot, he was incredibly excited. This was Sean. You guys might know Sean. And he was agitated, completely agitated in my office. And so I couldn't help but get agitated and excited. But I seriously, when he left the office, I was there by myself and I'm thinking, what the hell are we going to do with that? I had no idea what we were going to do with it. But it was his excitement that drove that discovery. It ended up being called a Sutrode. It's something that has the properties of a suture and an electrode. And that was his discovery, but it was also his enthusiasm for the discovery and what he thought could be done with it. That's what made the difference. So understanding the challenge and putting forward your innovative solutions, I think, is really important. That was a bit of waffle to go on to answer a very simple question. Sorry.
We have a few more minutes. Maybe the last question leave to Dan. You another wonderful.
Okay, thank you very much, Gordon. It's a great pleasure to see you here and also to listen to your talk. And I think 20 years ago, I worked in your institute, and from there, I already feel every time when I meet with you, either talk or the presentation, I always feel very inspired. I think you have talked about a lot of translation-related challenges or questions, and through the decades, I also think you always kept your science. Actually, you always stayed in the frontier of science or new science from, for example, the conducting polymers, graphene, and also biomedical applications. So maybe I think it's good also for students to hear from your side, how do you manage actually to stay enthusiastic about fundamental science as well? So you talk about a lot about the translation. That's very important. But for other aspects, I found it's also very inspiring from you is fundamental science. You're always very enthusiastic about science.
I think that must be genetic. Because I don't know why, but I certainly can't control it. And because seriously, like we just touched on a few little things today, but when you come up with different ways to process a material or discover a property of a material that no one has discovered before, or you come up with a characterization tool that no one has ever used before. I mean, there's an inherent excitement in that, because the key sentence there, the key part of that sentence, no one has done it before. I mean, that's an incredible privilege to get up every morning and go into the labs. And of course, it's not just, no, it's certainly not me. It's a whole group of us that work together. But every morning we wake up and a group of us go into the lab, and we're going to come home that night. And chances are we're going to know something that the world didn't know at the start of that day. We're going to know something that we're going to discover something that the world hadn't discovered yet at the start of that day. That's an incredible privilege. To be able to do that as a job, people pay you for it. It's amazing, and we're all very lucky that that's the job that we do for those that do research. It really is a privilege. There's an inherent excitement to every discovery, to the implementation of every discovery. And I think that's the other reason why I'm so, determined, if you like, that we get the translation bit right. Because all of those people that support us, fund us, pay us over all of those years, they deserve something back, right? And sorry, delivering a paper from Science or Nature under their door is probably not going to excite them, right? But giving them something that actually makes a difference to their life, and they've paid you to do it, that's exciting. But it takes fundamental discoveries and a commitment to translation, I think, to deliver the whole package. But yeah, and maybe it is genetic. I mean, both of my kids got into science and engineering as well. One's a biomedical engineer and the other's an electrochemical engineer producing hydrogen. So I would never say that at home. Oh, God, they're probably listening to this. Sorry.
Okay, thank you very much, Gordon. And, so I think this certainly is a wonderful journey, sharing not only your fundamental research, but also more importantly, and how to translate the knowledge and to next generation and also to real world, application. This actually make a real impact. So with that, I think we would like to close to this seminar, and thank you again for you giving this wonderful lecture, and also for sharing your experience in doing research and also doing the research translation. And please join me to thank Professor Gordon Wallace again for the wonderful talk. And we now invited the peer director, Professor Qingyan Chen, to the stage.
All right. Well, thank you very much, Professor Wang, for moderating this session. So Professor Wallace gave a very fine example of interdisciplinary research, from the chemical materials to the medicine. So to express our appreciation, we make this plaque, and with your title, etc. on that. I also like to invite two Professor Wang to come have another photo.
Thank you. Thank you very much.
Yeah, thank you everyone. And this seminar lecture is adjourned. Thank you.